Okay, so we've generated a gate level netlist now based on cells from the standard cell library. So initially during this first step of the synthesis, after elaborate, the first step after elaborating the synthesis process was SyncGen, where it created a netlist using generic logic gates. Now it has created that same logic using gates from the standard cell library. And these now here you see the appearance of an XNOR gate, because it turns out that the cadence rack standard cell library that we are using actually has an XNOR gate, but it has after the XNOR gate it has put two inverters in series, it looks like. So it has used an XNOR gate followed by two inverters in series. So that's the way it has implemented this logic. When we have run the synmap command. The synmap command is simply mapping the generic logic to gates from the standard cell library. But we can see it's not very optimal. It's used a very low drive XNOR gate XL, and for some sort of strange reason, it has used two inverters in series. After that, so it's used that's an unnecessary set of gates there. Those two inverters in series are unnecessary. But that's the way the synthesis tool works. It'll first create some implementation from using cells from the standard cell library. So in order to then make this more optimal, we use an optimization step finally, which is syn_opt. So we did elaborate, where we process the behavioral code. Then we did SyncGen, where we created a gate level implementation using generic gates. Then we did synmap, where we transformed that gate level implementation to implementation using cells from the standard cell library. And finally, we do syn_opt, which will optimize that implementation. So let's do that. And now let's see what the netlist looks like. So we do write_htl, and we see that it has cleaned up. It has removed those two inverters which were not necessary, and it has used an X4 gate instead of an XL gate. So it has used a high drive strength XNOR gate. So this is your final output of synthesis. We read the behavioral code, and we got an optimized or seemingly optimized logic circuit here using a single XNOR gate, which is what you would have expected, because if you would have done it manually using a truth table, you know that what you should optimally get is a gate level netlist containing only a single logic gate, which would be an XNOR2 gate, and that's what the synthesis tool has done. So we see it's working fine. Now the question is, why is it using an X4 gate? Okay, why is it not using some other drive strength? The reason is that it is unable to optimize, because if you recall, there was some warnings issued. There was no area attribute to the standard cells, so it is not able to. If I do report gates, it is not able to determine the area of the gates. So you can see that the total area is 0. Okay, and so what did this synthesis tool do? What did it do? It said, well, I've got all these different 2-input XNOR gates in the standard cell library. There are different drive strengths, and it has picked the gate which has the minimum delay, because we have not provided any timing requirements, and the tool does not even know what the area of the standard cells is. So the only thing it could do to optimize is to pick the logic gate, is to pick the 2-input XNOR gate which had the minimum delays, and that turns out to be XNOR2 X4. The standard cell library itself has XNOR2 XL, XNOR2 X1, XNOR2 X2, and XNOR2 X4. I think it has 4 different drive strengths for the XNOR gate. It picked the highest drive strength cell because that has the least delay. And it did that because we have not told the synthesis tool what the timing requirements are, and the .lib does not have the area of the logic gates. Okay, so I'm going to look at the dot lib and see why the area attribute is 0. So we'll look at grep minus A1 means look for a report a line after the matching line. I will look for cell space. And here's the dot lib. Bit two more. And you can see that all the standard cells have an area of 0. So this dot lib is not a very good dot lib. It is simply not specify the area of the standard cell library, and therefore the tool is unable to optimize. It's not optimizing properly. It does not know what the area is and not specify the timing. So it just pick the lowest delay cell. So let's correct this and let's provide the area information to Genus. Now the dot lib does not have the area information, so I will have to get it from somewhere else. And that somewhere else is the left file. The left file will have the area, and we know that we can provide Genus the left file as an optional input. If we do provide it, then Genus will obtain the area from the left file. And let's see if that makes any difference to the netlist that was generated. Current data is used in X4 cell. Okay, now we will redo synthesis, but not only will we read the Liberty file, we will read the left file as well. So I'm going to exit. Okay, so I will run Genus again. The first step is to read the Verilog behavioral code using the read HDL command. Which is this. Then I read the Liberty file. Then I will read the Liberty file. This is what we did last time, but now I'm going to also read the left file. So to do that, I use the command read physical. And here's the path to the left file. So I will use the command read underscore physical, which means I'm going to read some physical information. It's in the left format, so I'll do minus L minus left. And then I will provide the path to the left file, which is, that's the path to the left file. So it's read that as well. Oops. File not found. File. Okay, so now I'm going to read the left file, which is this file here. Okay, so now it's read the left file. So now we've read, not only after reading the behavioral code, we've read the Liberty file and the left file. Last time we had not read the left file. This time we're reading the left file because the Liberty file does not have the area information for the sensor libraries. It should have had it, but it didn't have it. So we are therefore providing the left file as an additional input to the synthesis tool. And now let's redo the synthesis and see if reading the left file makes any difference to the final output. So we say, so the first thing in synthesis is elaborate. And I'm elaborate in the circuit name is cell sense. And then the next step is to syngen, which synthesize to generic. We can see what it looks like. And you can see still the same as what we had last time, the 2 NAND gates and an OR gate. Then we will map to the standard cell library, so symmap. Let's again write out the Verilog gate level netlist. You can see that now it's using, previously it had done something using XNOR, XL and two inverters. Now it just used a single XNOR 2 X1. And then I will optimize it, syn underscore opt. And if I write HDL again, I see that it has used an X1 drive strength cell, okay, not the X4 drive strength cell that it had used last time. And that's because now it has area information and it sees that the X1 cell has a lower area than the X4 cell. If I do report underscore gates, we can see that now there's an area. It has used an X1 cell instead of an X4 cell. Okay, that's because the X1 cell has lower area than the X4 cell. Now we may wonder why it did not use an XL cell. There's an even lower drive strength cell available in the library. If that XL cell had a lower area than the X1 cell, it should have used that. So I would have expected the XL cell to have a lower area. I'm kind of intrigued by the fact that it has not used an XL cell but the X1 cell. Let's see why. We can look at the areas in the left file. So let's grep for a few lines after and a few lines. Well, let's grep for a few lines after the cell X nor 2 X1 in the left file. And we can see that this is the size of the X0 to X1 is 1.8 by 1.71. If I look for the size of the XL cell, let's see if it is less than the X1 cell or not. We should have expected it to be less, but perhaps it is not in this library. So we'll take XL. Okay. So you can see the X0 to XL has a size of 2 by 1.71. So strangely, in this library, the XL cell, which is a low drive strength cell, has a bigger area than X1, which should have had a higher drive strength. So there is something not quite correct in this library. The lower drive strength cell seems to have a larger area. So the synthesis tool has done the right thing. It has picked the cell with the smallest area. If I look at the area of the X4, let's say just out of interest, let's see what this is the cell it had used when we had not read in the left model. Let's see what the area of the X4 is. And you can see the X4 has 2.4 size. So it is a bigger cell, bigger width. The width is 2.4. All the standard cells are the same height. The height is 1.71. But the widths of the different drive strength cells differ. And X1 has a width of 1.8, XL has a width of 2, X4 has a width of 2.4, and so on. So X1 is mostly is very likely, or is almost certainly, the cell with the lowest area. In fact, just to make sure, let's look at the additional drive strength that we have, which is X2, and its area should be bigger than X1. If we look at X2, we can see that it's 2.4. So strangely, X2 and X4 have the same area. Okay, so this is library from Cadence. It's probably not a very well done library, and you can see that there are certain problems with it. But regardless, the synthesis tool has done the right thing. It has synthesized by using the cell with the minimum area. Now, we did not give it any timing requirement, and that's why it just simply went ahead and picked the cell with the minimum area when we asked it to optimize. Let's give it some timing information. Let's give it some timing requirements now. So to do that, we use this is just combinational logic. There are no flip-flops here. There is no clock signal. So we don't need to define a clock and a clock frequency, but we can specify using the set max delay command. This is what I'm doing here. A delay from the input to the output. So I'll say minus from, first of all, I'll set a max delay of some value. And let me see, I had figured out some good value to start with my synthesis script. Okay, so let's try 3.5 nanoseconds. So I'm going to set max delay of 3.5 nanoseconds from A to the output B. And I will set max delay 3.5 nanoseconds minus from the input S to the output B. So now specify the max delay from both inputs to the output. And let's optimize again, syn opt, and see if it changes the netlist. It's still using an X1. So this X1 drive strength is sufficient to give us a 3.5, to be within 3.5 nanosecond delay from inputs to output. So let's make the delay smaller and see what happens. When will it start needing to use a higher drive strength cell? So I will change the max delay to something much smaller. Let's set a max delay from S to B of, let's set it to just 1. And even from A to B, we will set it to 1. So now I've reduced the max delay from input to output from 3.5 nanosecond to 1 nanosecond, meaning I want the delay to be much lower. I want the cell to be much faster. Let me optimize with this new timing specification. So I'll do syn opt, and let's see what the new netlist looks like. It is still using X1. So even 1 nanosecond is good. X1 is good for even 1 nanosecond. Let's make this even smaller. I'm going to make this 0.2. And even from S to B, we'll make it 0.2. Let's optimize again. And let's write HDL. Still X1. If I do report timing, I can see that the delay from the delays, I needed 0.2, that's 200 picosecond, and the delays are only with 190, and the delay is only 194 picoseconds, so 0.194 nanoseconds. So I'm still good with the next one. Let's make it even less delay now. So if I change the delay to, let's say 0.1 from 0.2, I can see the delay is currently with X1, the delay from input to output is 0.194, as you can see here, 0.194. So if I say 0.1, then I think that the X1 cell will not have sufficient drive strength. The delay will be too high. It will need to use some other cell. Let's see if that happens. So I'm setting the max delay to 0.1. Okay. And even that was from S to A. Let's do the same from that was from S to B. Let's do the same from A to B. Now I will optimize once more, syn opt, to write HDL. And now you can see that logic has changed. It has used some very strange logic. It has used a NAND gate and an OAI gate. So it had to use a different structure of the logic in order to meet a delay of 0.1 that is specified from input to output. In fact, if I report timing now, previously with a single X1 XNOR gate, it had a delay of 0.194 from input to output. Now let's see what the delay is from input output. Now we see that the input output delay has gone down to 0.097. So in order to meet this 0.1 nanosecond or 100 picosecond input output delay, it could not do that using XNOR gates from the library. And it ended up using this very strange combination of gates. It ended up using a 2-input NAND gate followed by a AOI gate. And this combination generates the same logic as an XNOR gate, but with much less delay. In fact, if we look at the area now, using the report gates command, you'll see that the area which was previously 3 point something has now gone to 6.4. So as we started decreasing the input to output delay, at some point, the synthesis tool, when it was optimizing, had to restructure the logic from a simple 2-input XNOR gate to something different in order to meet the timing, and the area went up. In fact, we can try one more final interesting experiment. We can change the delay to something between 0.1 and 0.2. I'm going to make it 0.15. And let's see if that changes anything. So I've increased it from 0.1 to 0.15. I've said that the delay from input to output can be as much as 0.15 nanoseconds or 150 picoseconds. And let's see if that will cause the netlist to change that the synthesis tool generates. So if I do write HDL, it's still using the same thing. Let's try one last change to make it 0.19. I'm trying to see when I can get it to use an X4 gate. XNOR X4 gate. And if I do that, okay, so you can see it has reduced the drive strength from X4 to X2. Okay, because I've increased the delay, it is able to do it with lower drive strength gates, but it is still not using an XNOR gate. If I do report gates, you'll see the area has come down to 3.762. I want to somehow see why it is not using a drive strength for XNOR gate. Maybe that has a much bigger area. We'll have to see. Let's try again. 0.194. And we'll do one final syn optimize and see what new netlist it generates. It goes back to X0 to X1. So somehow when the delay is high, when you're ready to accept a high delay from input output, is able to generate the circuit using just an XNOR gate, which is what you would have expected from from the truth table that we saw. But it's using an X1 drive strength. As we start reducing the delay from input to output, the delay that we need for input to output, as we start reducing that requirement, the delay gets reduced. So the the logic has to get faster. And the synthesis tool is implementing faster logic by not using XNOR gates, but by using some combination of NAND gate and OAI gate. And the drive strength of those gates changes as the delays change. So as the delay gets very low, it uses X4 drive strength. As the delay increases from that point, it uses an X2 drive strength. And then when the delay is very high, it just goes back to using an XNOR gate. So what you can see is that if you provide a timing requirement and if it knows the area of the standard cells, the logic synthesis tool will optimize the logic in order to meet the timing with the minimum area.